Hello everyone. Today we will be doing M1 chapter 3 vectors in mechanics, and for this I will be following this book right here. So the first thing that we have to learn is the difference between a scalar and a vector quantity, particularly the differences between distance and displacement, velocity and speed. So first comes displacement. If you move a distance of 3 kilometers at a particular direction, you know your direction, maybe your direction is 10 degrees with the horizontal, then you are specifying your displacement. But here you're displacing yourself 3 kilometers to the north, and here you're displacing also 3 kilometers to the northeast perhaps. So in both these cases the distance is the same, that is 3 kilometers, but the displacement is different because the direction is different. So displacement is the distance plus the direction. Similarly, imagine that you're moving at a speed of 2 meters per second towards the right, and imagine that you're moving at a speed of 2 meters per second towards the left at some other time. In both these cases the speed is the same, 2 meters per second, but here the direction is towards the right and here the direction is towards the left. So here we have a velocity and here we have a different velocity, because velocity depends on speed plus the direction. So this is the difference between displacement distance, and speed and velocity. So what we can do is we can express these vectors in column vector forms or in ij notation. So for example, a notation of 2I plus 3j. A notation of 2I plus 3j would mean that I is basically the x-axis, j is the y-axis. So 2I plus 3j would mean 2 on the I-axis and 3 on the j-axis. So you would have a point somewhere around here, and this would be your vector. This is basically your vector of 2I plus 3j. Now in order to find the magnitude of this vector, what you have to do is you have to find the length of this line right here. So the length of this line can be found by using the Pythagorean formula. This much is 3, this much is 2. 3 square plus 2 square root over will give you the length of this line, that is root 11. So this is the magnitude of this line, the length of this line. So how do we apply this formula in our maths? If you look at page number 45, exercise number example number 9, we have a velocity 3I plus j. By the way, this can be written in the column vector form as 3 and 1. Okay, so this is the velocity. This is the velocity. We want to find the speed. So basically, speed is just the modulus of the velocity vector. What is modulus? Modulus means this x component square plus the y component square root over. This is basically the modulus. So if you had, for example, a displacement of x, y, for instance, there could be any number in place of x and y. This is the displacement. The distance would be the modulus of the displacement vector, that is the x component square plus the y component square root over. So this is how you get the distance from the displacement and the speed from velocity. Okay, so now in example number 9 we have found the speed. The speed is root 10. Now we want to find the distance moved in a time of 4 seconds. So the distance would be speed into time. Distance is equal to speed into time. So root 10 into 4. Don't confuse distance with displacement. Displacement is something that you get by multiplying the velocity into time. Distance is something that you get by multiplying the speed into time. So this is displacement, velocity into time, velocity vector into time, and this is your distance which you get by multiplying speed and time. Now you should be able to do exercise number 3C and 3A and 3B also. Now we will be moving on to situations where we can find the final displacement of a body, provided that we know its initial displacement, velocity and time. So we will have two sorts of situations. Suppose something starts from a displacement vector r0. So you have an origin here, origin O. Something starts at this point r0. R0 is the the initial position vector of a particle. It could be a particle, a ship, an aircraft. So this is the starting point of that particle. Now you want to find out what is the final position vector of this particle after it moves for some time. So definitely the final position vector will be the initial position vector plus the displacement. Okay, so for example, if this is my starting point O, if I was already 2 meters away from this point, this is my initial vector, initial point. If I was already 2 meters away, then I move a further distance of 3 meters, then what is my final position? My final position would be 2 plus 3 meters. Similarly, the initial position vector of a particle is r0. and with that we have to add the displacement vector to get the final position vector of that particle. So all these are vectors, so you need to underline them. So depending upon whether our velocity is constant, we are going to have two types of formula, which are, if your velocity is constant, then the displacement is given by vt, that is velocity into time. If your velocity is not constant, that is if you, or in other words, if you have a constant acceleration constant, then your displacement will have to be found by using the s to vat formulae. For example, s is equal to vt plus half at square, v square is equal to u square plus 2as, or s is equal to u plus v divided by 2 times t. So using any of these three formulae, you have to find the displacement and then input this displacement over here. So depending upon a constant velocity or a constant acceleration, you have to use this formula respectively. So we can see in example number 10 on page number 46, we have something with a particle starts from the point with the position vector 3, 7. So the particle starts from this point, therefore the initial position vector r0 is 3, 7. It moves at a constant velocity, so we have a constant velocity here, 2 minus I, and we want to find the position vector after 4 seconds, so the time is 4. I like writing my parameters down like this so that I understand which formula to use, and I don't get them mistaken when I'm putting them in the formula. So I need to find out the final position vector. So the final position vector is r0 plus the displacement, and we have a constant velocity situation, therefore the displacement will have to be found using the formula vt. Our r0 is known 3, 7, our v is known 2 minus 1, our t is known 4. Inputting all these variables, we can find the final position vector, which turns out to be 11, 3. I'm not going through the calculations because it is already done on page number 46, example number 10, but this is the concept behind that example. This formula can also be used in situations which have force and acceleration. Okay, basically vectors can be used anywhere whether these are velocities, accelerations, forces, displacement. So we have an example 14 on page number 47. Here we have a constant force of F. So this is a vector, and we don't know that force yet. That is something that we have to find. We have a particle of mass 2 kg, so m is 2, and our time is 10 seconds. So initially the particle is at rest, so u is equal to 0, and later it has a velocity, final velocity of 10 minus 24. So we have the initial velocity, final velocity t. We want to find f. So the formula for finding f, the first formula that comes to our mind for finding f, a resultant force, is f is equal to ma. We know our m, but we don't know the a. For finding a, we can use these three parameters right here. So which formula comes to your mind when you look at t, u, v and a? V is equal to u plus at. Our v here is 10 minus 24, which equals our u 0 plus a, that is something we have to find out, times t. Our t is 10 seconds. From there we can get our acceleration to be 1 and minus 2.4. So that is our acceleration, 1 minus 2.4. Using this we can find our force F. So F is equal to ma. We know our m is 2, and our acceleration is 1 minus 2.4. So our force would be 2 minus 4.8. That is our force. Moving on to the actual math which you will be facing in your exams. Page number 49, math number 11. So we have page number 49, math number 11. Basically this is your exercise 3D number 11. Exercise 3D number 11. So read the question with me. At 8 am we have two ships A and B, which are position vectors RA and RB from a fixed point P. So we have an origin P. From there we have two ships at 8 am, and the initial position vectors are given as RA and RB. The velocities are also given. We have to write down the position vectors of A and B t hours later. So let us first write down the position vector of A. Let us first work with A. So for A we know that the initial position vector Mind that here it is not written anywhere that RA is the initial position vector of A, but you have to understand it by reading the question. At 8 a.m. we have two ships, A and B. At RA is the RA I plus 3j kilometers. So this is the initial position vector of A, that is I plus 3j, or which can be written as 1, 3 in column vector form. And we have the velocity of A 2 minus 1, and we want to know the position vector of A after time t. So the position vector formula is R is equal to R naught plus displacement, and this is a constant velocity situation, so the displacement will be found using Vt. So R naught is equal to 1 3 Vt 2 minus 1, and our time will have a value of t. Okay, so 1 plus 2t, 3 minus t, 1 plus 2t and 3 minus t. So basically this is a general expression for the final displacement of A after time t hours. So if you want to know what is the position vector of A after 2 hours, you input 2 in place of t and you get the final position vector of A after 2 hours. So similarly we can find the position vector of B. Let us list down the things that we know about B. The initial position vector of B is 5 minus 2. The velocity of B is minus 1 4. And we have to find the position vector at time t. So R is equal to R naught, which is 5 minus 2, plus Vt. Our V is minus 1, 4, and our t is t. So 5 minus t, minus 2 plus 4t. This is the final position vector of B, RB and RA. Right, show that t hours after 8 a.m. the position vector of B relative to A is given by this vector. So we have just done part A. Moving on to part B. So we have to find the position vector of B with respect to A. Okay, relative to A or with respect to A. So the position vector of B relative to A means the vector A B. This is the meaning of the position vector of B relative to A. Right. So AB vector means BO minus OA. Okay. BO minus OA. Let me get this. Let me write this down in a more elementary form. So AB vector, we know the vectors OB and OA. Okay, how do you know those vectors? We know the final position vectors of B and A. So this vector is basically OA, which is the position vector of A from the origin O. Here the origin is described as P. Here the origin is called P, but you can also call it O. Usually the origin is called O. So this vector that you have here, this vector is our PA vector. Okay, and this vector is our PB vector. Basically the position vector of B from our origin. This is the PB and this is the PA. So we have two vectors, PB. We have our origin at P, we have PB and PA. Now we want to find the vector AB. So if you want to go from A to B, you have to go from AP to PB. AP to PB. Okay, fine. AP to PB. Right. So AP we don't know, but we know PA. So if we change the direction from AP to PA, we know that we have to put a negative sign in front. PB will remain the same because we know the expression for PB. So PB is here, right? So minus PA. Our PA is this, that is 1 plus 2t, 3 minus t, and our PB is given by 5 minus t, minus 2 plus 4t. From there we can see that our final vector is 4 minus 3t and 1 plus 3t. Oh, sorry, this is minus 5 plus 5t, minus 5 plus 5t. So there was a calculation mistake. So this is what the question wanted us to show, and we have shown it. Show that the two ships do not collide. Okay, for this part what you have to show is, right, so for two things to collide they have to be in the same place at the same time, right? So this is the displacement between the ships AB. Okay, so this is the ship A, this is the ship B, and AB is the distance between the two ships. So this is the displacement vector of those between those two ships. So whenever this displacement whenever this displacement will become zero, at that time the two ships will collide. So for this whole thing to become zero, our I component will have to be zero, which is 4 minus 3t is equal to 0. From there we get a value of t to be 4 by 3. Similarly, our j vector will also have to be 0. This is the j vector, that is minus 5 plus 5t is equal to 0. From there we can get our value of t to be 1. As you can see, the value you obtain from the I vector is not the same as the value obtained from the j vector. This is why the ships will not collide. Two particles or two bodies will only collide when the time obtained from the I vector is the same as the time obtained from the j vector. So your answer should be t, the t obtained from the I vector is not equal to the t obtained from the j vector. Therefore, the two ships do not collide. You have to write this sentence down in order to complete your answer. So find the distance between A and B at 10 a.m. So first of all, we started our journey at 8 a.m. So at 10 a.m. we have a time gap of 2 hours. So our value of t will be 2. This t here that you can see, this t starts counting from 8 a.m. onwards, and this t is in hours. So from 8 a.m. to 10 a.m. we have 2 hours, so t is equal to 2. So if we input the value of 2 in this equation, in this expression, then we can get the displacement vector between A and B. So AB displacement vector is given by 4 minus 3 into 2 and minus 5 plus 5 into 2. This is the displacement. So minus 2 and 5. Basically, this is the displacement between the two ships at 10 a.m. But they told us to find the distance between the two ships. This is the displacement vector. So to get the distance, you have to do this. I component square plus the j component square root over. So 4 plus 25, that is root 29, which turns out to be 5.39. This is our distance between the two ships at 10 a.m. So be very careful about the displacement between the two ships at 10 a.m. and the distance between the two ships at 10 a.m. The last part of this video will be a more difficult math from your review exercise, chapter review 3, page number 52, question number 9. So this is page number 52, question number 9. So please read the question with me. We have two ships P and Q traveling at constant velocities. Okay, so at midnight, that is 00 hours, P is at a point with position vector this relative to the origin O. At the same time, that is at midnight, Q is at this position vector minus 1626. 3 hours later, P is at the position vector with this. The ship Q travels with a velocity of this. So basically, we have the final and initial position vectors of P, and we have the velocity of Q. At time t hours after midnight, the position vectors of P and Q are given by small letter p and small letter q. We have to find the velocity of P in terms of I and j. For finding velocity, you need to know the final and initial position vectors. So R is equal to R naught plus Vt. This formula will apply for P. Why? Because both P and Q are traveling at constant velocities, and this is a constant velocity formula, Vt. So R is equal to R naught plus Vt. We know that after 3 hours, the final position vector of P is 25, 24. This is the final position vector of P. And the initial position vector of P, that is at midnight, was 10, 15. And the velocity of P we don't know, that is what we have to find out. And 3 hours. So since T is given in hours, you can read at the line, at time T hours after midnight, the position vectors of P and Q. So T hours, T is given in hours. So our T is in hours. So here the question says that this is the final position vector of P after 3 hours. So T is equal to 3. From there, our velocity vector of P will be 5, 3. This is the velocity vector of P. So this was our part A. In part B, we have to find the expressions for P and Q in terms of T, I, and J. So we know that we know the velocities of P and Q. We know the initial position vectors. So using those, we can find the final position vector. So small letter P and Q are basically the final position vectors of P and Q. So for P, the final position vector will be equal to the initial position vector plus Vt. So the final position vector, which is given by small letter p here, initial position vector, which is 10, 15, plus the velocity, which we just found in part A, 5, 3, t. So 10 plus 5t, 15 plus 3t. This is the final position vector of P after time t hours starting from midnight. Similarly, for Q, we will use the same formula, R is equal to R naught plus Vt. We are using Vt for displacement because the ship Q is moving at a constant velocity. The initial position vector of Q was minus 16, 26, right? And the velocity of Q is 12I, so that is 12, 0. This is the meaning of 12I and t. So that will give us minus 16 plus 12t and 26t. This basically. So these are the position vectors of P and Q in terms of t. And if you want, you can express these in terms of I and j. This is the I vector, this is the Q j vector. You can express them in terms of I and j. Right, now at time t hours after midnight, the distance between P and Q is t. By finding an expression for PQ, show that d square is equal to this. So part C, by finding an expression for PQ. So first of all, we have to find an expression for PQ. PQ is given by PO minus OQ, or which is minus OP minus PO plus OQ minus OP plus OQ. So minus OP. OP is basically the displacement vector of P from the origin, which was given by small letter p right here. So don't get confused, this OP is basically the small letter p. If you analyze carefully, OP basically means the displacement of P from the origin, and that is basically P, what we found here. So minus P, that is minus 10 plus 5t minus 15 plus 3t plus OQ, which is minus 16 plus 12t, 26t. Not 26t, only 26, my bad, only 26, right? Now 10 minus 16, that is minus 10 minus 16, that is minus 26, minus 5 plus 12, that is plus 7. So minus 15 plus 26, it is 11, minus 3t. Okay. So this is basically the displacement between the two ships P and Q. From here we have to find the distance. We know that this distance is given by the square of the, basically the modulus of the displacement. It is minus 26 plus 70 square plus 11 minus 3t square. So if you expand these brackets and if you work them out, then you will get this expression 50t square minus 430t plus 797. Basically what the question wants us to show. So first of all, we found the displacement vector between P and Q. From the displacement vector we found the distance. Given that when t is equal to 2, okay, so we have a passage. Weather conditions are such that an observer on P can see the lights on Q only when the distance between P and Q is 13 kilometers or less. So basically, this is the expression for d square. So this is the expression for distance square. So the distance will be given by 58t square minus 430t plus 797 root over. So the lights from Q are visible from P only when the distance is 13 kilometers or less, which is d, when d is less than or equal to 13 kilometers. Basically, 58t square minus 430t plus 797 less than or equal to 13. If you square both sides, you get this expression 58t square minus 430t plus 797 less than or equal to 169. Now if you bring all the things on the same side, minus 430t, you get 628 less than or equal to 0. So now if you want to find the critical values of this quadratic expression, we have to equate this quadratic equation to 0. From there we can get our values of t to be, let's use the calculator. .41 and 2. So basically this value 2 was already anticipated in the question. So given that when t is equal to 2, they come inside of one another, and basically when t is equal to 5.4, they move away from one another. Okay, so when t is equal to 2, the first come at a distance of 13 kilometers away from 13 kilometers away from each other. From t equal to 2 to t equal to 5.41, they are closer than 13 kilometers. At exactly 5.41 t, they are once again at a distance of 13 kilometers away from each other, and after 5.41 they start moving away from one another. So this is what's going on. At t equal to 2, they come exactly 13 kilometers away from one another. From t equal to 2 to 5.4, they are closer than 13 kilometers. At t equal to 5.4, they are once again exactly 13 kilometers away, and after 5.41 they are once again moving away from one another more than 13 kilometers. So we have to find the time to the nearest minute at which the lights on Q move out of sight of the observer. So we have to find the time after midnight when this is happening, 5.41. So the time, we are passing 5.41 hours after midnight. So this time 5.41 is 5 hours plus 0.41 hours. The whole thing was in hours. So 5 hours is okay. We have to convert this 40.41 into minutes. So you have to convert this 0.41 into minutes by multiplying this 0.41 into 60, which gives us 24.6 minutes. I'm going to round that off to 25 minutes. So after 5 hours and 25 minutes after midnight, the ship Q moves out of sight of ship P. So we started at 00 hours, midnight. After 5 hours and 25 minutes, the ship Q moves away from the site, and the time on the clock at that time is 05:25. This is your final answer. So there are many such maths in this chapter. I was not able to cover all those maths. If you need help with any particular math, you can book a session with me on Fiverr. I'll leave the comment in the link in the comment section below. If you found this video useful, please subscribe, press the bell icon, and comment something positive so that I get motivated to make more videos for you. Thank you very much for watching.